All right. So. Let's see what we've got here to do. All right. So, graphing quadratic equations. There are kind of three major forms with which we will want to be familiar, okay, and kind of be comfortable moving between or among. All right, the first one is the one we worked with the most so far, I would say, and that is known as standard form. Okay. The designation, I don't think, is like so important. I mean, it's not like I'm going to test you on like knowing that, oh, this thing's standard form, I think, but standard form is, so again, for A, B, and C are numbers. I'll say real numbers here in this case. Okay, and so we end up with then, of course, that's the ax squared plus the bx plus the c equals 0 there. Or I guess I should really put, sorry, not equals 0. Let me just use f of x, because we don't know what it does. It doesn't have to be equal to 0. So there we go. Standard form. That's what we've been working with. Okay. And so if we want to graph a quadratic equation from this form, we have a couple options, right? Option 1, right, is we could just pick some x values, plug them in, get the matching y value, and then, kind of go from there. But of course, right, there are like parts of our quadratic equation that maybe are helpful to find, right? You know the shape is going to be something like this, right, or like this, depending on whether we have a positive a value or negative a value there, right, that parabola. And so typically from this point, right, we try to, it's helpful to like find important points, for example, like this point right here or here, and what do we know that point is called? Or what is that point called? The vertex, right? Okay, it's the vertex. And so from this point, right, it's not, we can't just like necessarily pull the vertex out from this, but there are strategies to find the vertex. One strategy for finding the vertex, or at least the x-coordinate, okay, of the vertex. Anyone remember? What do we use there? X is equal to what? Yep, negative. Negative b over 2a. Is that what you're going to say too, Andrea? Negative b over 2a. Yep, exactly right. So you take that coefficient of the x term divided by twice the coefficient of the x squared term, and of course make it negative there. Do you recognize that negative b over 2a from something? Yeah, Cooper? It's in the quadratic formula, right? So that front half of the quadratic formula. Exactly right. Okay, exactly right. And so that quadratic formula there is using that kind of like the x-coordinate of the vertex, and then we're adding to it and subtracting to it the, oh shoot, what's that called again? The square root. Discriminant, thank you. We're adding and subtracting the discriminant to it to then find our zeros, because the zeros are symmetric about that x-coordinate for the vertex there, right? So there it is. Okay? And so that locates the vertex, or the x-coordinate for the vertex. So then that gives us the x-coordinate, but of course the vertex also has a y-coordinate. What do we do then to find its y-coordinate? Yeah, plug it into the function there, okay? And so then f of negative b over 2a, that is the y-coordinate, okay, of the vertex. Right, pretty straightforward stuff there. So let's go ahead. How do you guys do this? So you guys try this one. I won't even do it. All right, find the coordinates, or sorry, find the coordinate of the vertex of, and let's say 2x squared minus 8x plus 6. Okay. So go ahead, use what you know there. Find the vertex of that quadratic there. like a little fortune teller thing. Yeah.
Yeah, I was like, yeah, then I realized, yeah.
Say again? F. Function. What is our function? Just plug it back into the function.
This is what you do as an SSL. This is what you do as an SSL.
Plug 2 back into the quadratic equation. There's no numbers or anything on it. How do you know what to do? I mean, there's no like, oh, I see. I'm just supposed to say something. Like,
I'll figure it out. I'll write it down.
I was gonna say you gotta put the stuff on it still. You gotta label that.
This is what you do as an SSL.
All right. Yeah. Crafts. Actually, yeah. Emma Swilinski made that. She said that she found it on Pinterest and made it. So.
What's that?
Okay. Not with that attitude. All right, Matt. Matt, what do you say there? What are the coordinates for the vertex of this parabola? 2, -2? Sounds good to me. Okay. Anyone need to see that done? No one? Well, I'm going to show it to you anyway here. So x equals -b over 2a. So our b is -8. So -8 is +8 over 2 times a. 2 times 2 is 4. So we get x is 2. Right? And then we just evaluate. And I know that like it's weird to like, how do you show plugging into? So I mean, sometimes we just like, we just write it. We just write like 2 times 2 squared minus 8 times 2 plus 6 like that. But there is actually like a mathematical way, right? It's easy when it's a function. You just like replace the x with a 2, and that shows that you're plugging into the function. But when you just have a y, there's no like parentheses there to show substituting it in. So how are we showing that we're evaluating y at 2? There is a way to do that. Use like a little vertical bar like this, and then you put x equals 2 like that. And that means y evaluated at x equals 2. Okay? That's, again, is it important that you know that? Not necessarily. It's helpful if, again, if you plan on going to calculus, we'll be using that notation in calculus some. So if you plan to do that. So anyway, that's helpful to see that. When you simplify there, you get 2 squared 4 times 2, 8, minus 16 plus 6. So 2 minus 6 is -14. -14 plus 6 is -8. I made an error here. 2 times 2 squared. There you go. 2 squared is 4 times 2 is 8. Fixed it. Okay, and so then 8 minus 16 is -8. Plus 2 is -2. Okay, so there's that, and there's that. Okay? So let's actually kind of sketch a graph of y equals 2x squared minus 8x plus 6. Okay? So we'll get our x and y coordinates here, or xy axes, I should say, drawn. Again, we're just going to do a sketch. We could be more precise if we wanted to with like graph paper and stuff, but I'm okay with just doing a sketch for this stuff right now. Okay, so we'll plot that coordinate of 2, -2. So I'll say something like that, something like that. Okay. Okay. So what we did here, right? We found the vertex using x equals negative b over 2a, right? And then, or I guess I'd say, and f of negative b over 2a as well. Okay, so we plug that negative b over 2a into the function, or evaluate it at the y. But of course, that's only a single point, right? So how can we go about getting more points here for our graph? What should we do? Yeah, Julie?
You find the zeros.
Okay, so option 1, right, we could find the zeros, okay? So let me ask you this question. Let me take a step back. Will every quadratic equation have a vertex? Will every parabola have a vertex? Yeah, right, it's going to have a vertex. Will every parabola have zeros? No. So you can absolutely use zeros as points, but you want to be a little bit careful because sometimes you won't have those zeros, and so it's like, oh, okay, you know. So we could do that, though, absolutely. So we could just, you know, find the zeros, okay? I could also just say, though, we'll just pick some x values, right? Because certainly we know the domain of this is what? It's all real numbers, so we should be able to plug in any x value we want and then get some points from there. My recommendation is just pick some x values. Near the vertex, right? And I know this is like not rocket science here. To graph. Okay? So going back to, you know, what you did when you first learned how to start graphing things, right? You just picked some x values, plugged them in, found the matching y values, and then plotted those points, and then connected the dots, right? So let's do that here. So we had an x value of 2, so let's, again, try like x equals 3 maybe, okay? So evaluate y at x equals 3. Okay, so again, that means y evaluated at x equals 3. Okay, and so you say 0? All right, so you say, yeah, 3 squared is 9, times 2 is 18, minus 3 times 8, which is 24, so negative 6 plus 6 would then be 0. Okay, so you get the point there, 3, 0. All right, so 1, 2, 3, and then a 0. Easy enough. Okay. We also notice a particular behavior, we're going to utilize a particular behavior of quadratics, that they are symmetric, right? And we'll talk about that axis of symmetry here in a little bit. Okay, I don't know why. Well, you can see that it's going to be symmetric, right? These things are symmetric. There's an axis of symmetry. I'm not going to have you worry so much about identifying the axis of symmetry. Oh, I guess I can. Okay, well, anyway, later. But for right now, anyway, because we have this point right here, right, then reflect that over that axis of symmetry that's going to go right through that vertex there. We're going to end up with a point right here as well. Okay, so if we have the point 3, 0, we'll also have the point then 1, 0. Okay. And then let's do one more here just for fun, okay? So let's say like x equals 4. So 4 squared is 16 times 2 is 32, minus 8 times 4, which is another 32. So 32 minus 32 is 0, and we're left with 6. So I'll try and graph this here. Let's see here. 1, 2, 3, 4, 5, 6. And we'll say 4, so like right there. And then by symmetry, we're 2 away, right, from the center of our parabola. So we'll go 2 away in the other direction, and we'll be on the y-axis there. And that's enough points, I think, to get the graph. Like so. Okay. So that's standard form. Right? Standard form of a parabola using negative b over 2a. Questions on any of that? Questions on any of that? Easy peasy. Okay. But yes, the zeros are absolutely a way to go there, Julie. I mean, if you want to find the zeros and do that, that's fine to do it too. Okay. If you want to factor in stuff like that, it's an easy way to do it. Okay. Let's keep going then. We've got 2 more forms to look at here. Okay. We'll also look at vertex form. Right, okay. Again, blast from Algebra 2's past. So that's y equals a times the quantity x minus h squared plus k. Okay. So we kind of worked with something with this form before too. If you remember back when we did transformations, right? We took our parent function x squared, just plain old x squared. We shifted it right and left, up and down, and that resulted in that, the h was a shift right or left, right? The k showed us a shift up or down, and so that was, part of that unit, right? But we're seeing it again here because, well, the parent function x squared, where is its vertex? So x squared, just the graph of plain old x squared, where is its vertex located? Julie? Well, just x squared. So it would be like 0, 0 is what everyone said, right? 0, 0, because it's just plain old x squared, right? Then when you shift it left or right, well, if you shift your vertex that's at 0, 0, if you shift it right h units, that means you're going to be just moving, your x coordinate to the right that many units, right? Or you shift it left a certain number of units, it's going to go left that h number of units. Or up or down, again, it's going to adjust your vertex. So the vertex is literally just the shift there. The vertex is just literally the shift. Okay. No need to do negative b over 2a. In fact, we don't know what b is in this case unless we FOILed out the x minus h, right, and then distributed the a, and then combined all of our terms there and stuff like that. Right? Then you can figure out what b was. But right now, all we know is the a, right? This a here, that's the same a that we were talking about before, where it was ax squared plus bx plus c and stuff like that. Okay. All right, very good. I think I know what happened here, or maybe I don't. Maybe I don't. Never mind. Okay. So then, let's see here. We'll also again let's see. Some other things we want to be familiar with here, right? That a, for example, if a is greater than 0, right? That just means that our parabola is going to look like this. If a is less than 0, that means our parabola is going to look like this, like a frown, right? We got the smiley face, we got the frown. Okay. I know in Algebra 2 you guys maybe went more in depth into what that a value does too. I'm not going to worry too much about that here for pre-cal. We're just trying to make sure we got the basics, some of the basics down. Because it's not. I mean, it's important that we can graph it still, but it's not so important that we can describe the transformation in that sense. It's not going to be so important. Okay. So let's see here. How about we try one? Okay, so let's graph y equals -1/4 x plus 2 quantity squared plus 5. Okay, just as an example here. Okay. With this information, what is the vertex of our parabola here? Careful, not positive 2, 5. Right, negative 2, 5, because again, it's x minus h, right? We have a plus 2, so in order for that to be a negative, in order for it to be x minus h, we have to think of that as x minus a -2. Right, so x plus 2, it's be careful, it's really a -2 is our vertex's x coordinate. Okay, and then the y coordinate is, though, 5. Okay? And so let's go ahead and graph this, and then we'll plot that vertex. So let's see here. So 1, 2, 3, 4, 5. So -2, 5. There's our vertex. And again, we could, find our zeros here, for example, and do it that way. All right. We can also just, again, pick some x values, plug it in. It's really, kind of your choice what you, want to do here. I'm gonna just pick some other x values here. So let's, for example, just try. Let's make it easy for ourselves and do x equals 0 here. I see that's going to work out nicely, actually. Okay. So 0 plus 2 is 2, squared is 4. 4 times -1/4 is -1, plus 5 will be 4. So at 0, we are at the y value 1, 2, 3, 4, right there. And so by symmetry, that's 2 units away in the right direction here. So if we go 2 units away in the left direction, we'll also have a point at negative 4, 4 as well. Okay, and let's see here. I think another nice one works out if we use a 2 here. So let's use 2 as well. So 2 plus 2 is 4, squared is 16. 16 times negative 1/4, negative 4, plus 5 is negative 1. Wait a minute, I do that math right here. 2 plus 2 is 4, 16, negative 1/4, negative 4, plus 5, positive 1. There we go. Okay, so 2, 1. And then, of course, that is 1, 2, 3, 4 units away from that center, that axis of symmetry there. 1, 2, 3, 4. So we'll go 4 in the other words. 1, 2, 3, 4, and at the 1 there. Okay, and that's enough points right there, I think. Like so. Okay. Let me give you one more here, and then I'll have you guys try 2 on your own here. All right. The last form we're going to look at here is intercept form. All right. Okay. So intercept form, that's when you see it kind of written in this format. Which we've seen before, right? That's what happens when we factor our quadratic. We end up with something like this. Okay. Yeah. Okay. So the x-intercepts are easy for us to find, right? This is called intercept form because we set this equal to 0 and solve, right? When setting it equal to 0 means we're going to have y coordinates that are 0 there. So we'll end up with then p, comma 0 as our x-intercepts, and q, comma 0 okay, as our x-intercepts there too. Okay. So now, the x-intercepts, right, are, because of the symmetry, they're kind of like they're, I guess, both equidistant from that axis of symmetry, right? So how can we use our x-intercepts to maybe locate the middle part there of our vertex? What could we do? So yeah, Parker? Midpoint. Yeah, the midpoint, okay? And really, we don't even need to worry about using the midpoint formula. We just need to find the middle point between the p and the q, right? So yeah, the vertex then, or again, the x-coordinate of the vertex. All right. It is merely x equal to p plus the q over the 2. Like that. And then we know how to find the y-coordinate then. We just plug this back into the original quadratic there. Now it'll get you that matching y-coordinate. So we'll do an example here real quick. So we'll graph y equals x plus 3 times x minus 1. Okay. So the zeros for this, or the x-intercepts, right, given this format, what are the x-intercepts going to be? We're in intercept form, right? So what are the intercepts going to be here in this particular problem? Right here. Yeah, Ramike. Yep, negative 3, 0, and 1, 0. So if I was going to graph this, right, I could go ahead and just plot those. So we'll say negative 1, 2, 3, and positive 1. Okay. So there are our 2 zeros. Okay. And like Parker said earlier, we can find the midpoint then of those two, so we'll add them up. Okay, so the vertex calculation here, we'll do -3 plus 1 over 2, which is -2 over 2, -1. So our vertex has an x-coordinate of -1, comma, and then we've got to find that missing y-coordinate, which we'll then just plug in here. So y evaluated to x equals -1. And so we get 2 times -2, which is -4. Okay, so -1, -1, 2, 3, 4, right there. All right, and I'm not going to bother finding more points there. I think that'll be good enough for that. All right, and again, we have that nice little axis of symmetry right there. Okay. Questions on any of that? Right? Yes. Ryan?
For like the coordinates and everything, usually like it's like 5. It's like on like a quiz or a test.
Right.
You always have to show 5.
So I would say if the directions don't specify, then give me enough to get the the shape of the graph that you need, kind of thing. Okay. But yeah, typically I think 5 is like a good way to go, just because 3 can be enough. I mean, here you kind of have enough with the 3, but it is helpful sometimes I think to have 5. But yeah, if it doesn't specify, I'd say bare minimum. The vertex and then 2 other points, I would say, and you can use the symmetry there. That'd be bare minimum, I would say. Okay. So yeah, let me give you 2 to try here then. All right, I'm just going to put mine here on the side. All right, so I'm going to have you graph y equals x squared plus 2x plus 1. I'm off the screen. There we go. And then also graph y equals negative quantity x plus 3 squared plus 5. Okay. So, first one here should look something like that. Okay. Your vertex, get again from a couple different ways there or whatever. This one you could have actually factored and gotten the vertex too, right? So negative b or just use negative b over 2a. Get your x equals negative 1 there. And then I got a few more points and use symmetry to get the rest there. Okay. Let's see what's in the house. That's fine with that. Any questions on any of that? It's pretty straightforward stuff. Simple, simple, simple. Okay. And then how about this one here? There's the next one. Okay. Vertex was in vertex form, so it's super easy to graph there. Negative 3, 5, right? We have a negative a value there, so we know it's going to be like a frowny face. All right? And I got some more points. Negative 2, 4, and then negative 1, 1. Okay. One thing I did want to point out here too is the identification of extrema or extreme values, okay, of a graph. I'm going to do that here real quick. Actually, let's make sure. Any questions on these two graphs here before I move on? It's important that we're okay with that stuff. So I just want to talk about extreme values here, or extrema for the plural variety. Okay, I'm just going to add this in here, and that'll be it. We'll get you guys started on your assignment. Okay. There are two kinds of extrema that it'll be helpful for you to be familiar with. Okay. The first one is relative. First kind is relative extrema. Okay. The idea about relative extrema is that these are, extreme values kind of like within a neighborhood of points. Okay. So a relative maximum, right? So extreme values, you can either be at a maximum, right, kind of like a highest point, right, or you could be at a minimum, like a lowest point. That would be like your extremes, right? Highest, lowest. Those are the extremes kind of thing. And so we can talk about these things. Okay. So a relative maximum, you can think it occurs at, and I know I'm going to just kind of describe this. It's easier to describe it just like visually as opposed to like trying to going through like the mathematical definition for it. So we'll just say it occurs at a hill/peak. Okay, at a hill/peak, right? Not a kill/peak. Hill/peak. A relative minimum then. Oops, can't spell occurs without two C's. Okay, a relative minimum occurs then at a valley, you could think. Okay, in the graph. I dip down there. Okay, and there is a mathematical definition for it, but it's more complicated than we need to worry about. Okay, so for example, looking at our previous graph right here, right? Do we have a relative minimum for this graph right here? No, right? Okay, we don't have a valley, but we do have a hill or a peak here, right? It's right here, okay? And so what is located at our relative maximum here? What other point is located at the relative maximum? The vertex, right? And for quadratics, right? For quadratics, the vertex will either be a relative maximum or a relative minimum, right? It's going to be one of those two things, okay? But we'll see later that there's going to be relative maximums and relative minimums, okay? There can be more than one kind of thing, but of course for a quadratic, it's not too crazy stuff going on here, okay? So it doesn't really, it's not, it's kind of hard to distinguish. When we get to the polynomials, we'll see more about relative maximums and relative minimums, okay? But we also, does every graph that we've seen so far, or can you give me an example of a graph that does not have like a relative maximum or relative minimum simultaneously, right? So maybe something we've seen before that doesn't have either a relative maximum or a relative minimum. What kind of graph might not have either of them? So yeah, Megan, what do you say?
Linear.
Okay, linear. Cooper, what are you going to say?
Cubic.
A cubic, okay. Could be both of those actually, yes, could be. Some cubics, every line will not have a relative maximum or relative minimum, and some cubics don't too, you're right. Okay, that's true. Like x cubed, for example, wouldn't.
Yeah.
Yep. Okay, now, There's another kind of extrema I told you about, and those are called absolute. And again, we'll say absolute maximum and absolute minimum. Okay. And here's where it gets a little fuzzy, because both absolute extrema and relative extrema, they're dealing with extrema, right? Extreme values. They both have maximum minimums. Sometimes, right, they are the same point. So sometimes an absolute maximum will also be the relative maximum. Sometimes a relative minimum will also be a relative minimum. Okay? But it's not always the case. And vice versa. Sometimes a relative minimum won't be an absolute minimum kind of thing. But sometimes they are the same thing. Okay? Of course, you will never have something that's an absolute maximum be a relative minimum. Or you'll never have an absolute minimum and a relative maximum at the same time. That's just not possible. Okay? So what makes something absolute, right? So here we say a relative maximum occurs at a peak or a hill. So what would make it absolute? Well, an absolute maximum is the highest point. And again, I'm introducing this idea now when we really can't distinguish between the two, right? Where is the absolute maximum located on a quadratic? For example, on this quadratic, where is the absolute maximum located? Also the vertex, right? And so it's hard to tell the difference. But again, as we get into polynomials and stuff like that, it'll make more sense. So it's the highest point, and so the absolute minimum then is also then the lowest point. And again, there's more official mathematical definitions for those, but I'm not too worried about them right now. Okay? And the idea about relative and absolute, right? Relative, the idea of relative is in relation to other points around it. A relative maximum is the highest point in that neighborhood of points. A relative minimum, likewise, in a neighborhood of points around it, it's relatively the lowest point. Absolute maximum, though, means it is absolutely the highest point, right? An absolute minimum, it is absolutely the lowest point, kind of thing. So that helps distinguish it, too. And again, we'll see more of this distinction later as we talk about graphing polynomials and things. But for right now, the best we can say is what best we have is the quadratics. Okay, and we'll identify it that way. Okay, so just being able to identify those things too in our graphs as well. I just wanted to introduce that idea here. All right, I think I've got everything I need to cover there. Any questions on any of that? So I think I'll get you guys started on your assignment, and then you can maybe ask me some questions if you need to from there. Okay, so let me get you that assignment.
It's beautiful.
Did you ever story about the person who was was a boy or a girl, I think, that was sick and wanted to make 1,000 paper cranes or whatever?
You want to shut up?
So, all right. On page 132, numbers 7 through 12, 37 to 39, 76 and 79. Okay, 76 and 79, by the way, are calculator active. You may use a calculator for those. Say again? Potentially, yes. Excuse me. Yes. Thank you. Thank you. A regular breakfast burrito? We'll see.
That just took me 20 minutes. 1,000 paper cranes.
1,000.
That's a lot.
You'd probably get faster though too. You know what I'm saying?
Yeah.
But then you got to factor in paper cuts.